we're only getting a handful of those red dots on the far left-hand side. As I said, this just proves that we're finding interesting patterns. We're effectively creating these really tight clusters in the high-dimensional space. So let's look at some real attacks. So same sort of presentation here. The blue is the actual attacks. The red are the legitimate examples. The reason you don't see 33 attacks here is when we put together this workload, the attack team didn't know what the legitimate workload looked like. So more often than not, they came up with some sort of query that they wanted to run that ended up having something completely anomalous about it and therefore being rejected trivially. So 22 of them were thrown away with a score of 0. And then of the remaining 11, they didn't get anywhere close to our threshold of 99.25. So if we're setting our threshold that way, we're in fact catching every single real attack, and the results were showing that we had about a precision of about 99% if there was an even number of attacks to legitimate cases. Hopefully in the real world your number of attacks isn't as high as your number of legitimate queries, so you will see a bunch of false positives as a result of doing something like this. And what actually happens is going to depend really on how heavily adversaries are banging on your system. And the one we were looking at, it's not accessible to the outside world, so the only people who can attack it, we think, are internal employees, and we hope that we don't actually see any of that. So it's a little hard to know exactly what would happen in the real world, but we think that we really have some good results there. So let me demonstrate what happens then in the real system to bring back to that original demo. So what we've got is the exact same web interface, but we've now plugged our software into the database on the back end. So when we run this query with the single quote, semicolon, dash, dash, the web application returns the connection is dropped, and so it says malicious activity was suspected. I'm not even going to process this particular query. So why does that work now that we've seen everything that was going on behind the scenes? Here's the actual decision tree that we built for a particular feature, which is the complexity of the where clause. So when we look at the query that gets assembled, select everything from core where ID equals this, and we've commented everything else out. The complexity of the where clause, according to the optimizer, is 7. And why is it 7? I have no idea how ID equals my name is 7. That's the number it returns. A little bit of magic. But if we walk through this decision tree, the first thing we have to ask is, how many columns are being returned by the select clause? It's 129. We knew that from the attacks. So we follow this branch. 7 does not fall within this 11 plus or minus 0 range that we've identified as being what we expect to see. So the attack fails. What happens if we're a super user? We can now run any query we want. We don't have to rely on SQL injection attacks. And as an insider, I know that the system has all of these sorts of extra features in. It's built up the profiles, and it's trying to stop me. So as an attacker, I say, well, I'm going to need to get the where clause to look pretty much right. So instead of trying to run just the ID, I'm going to throw in this extra little bit to the query that I know from some other means, or I could just test each one of the states until I found the right one. Let's see if that works. Unfortunately, through its optimizer magic, the complexity of this one is only 10. It's missing something. So when I run through it, I end up seeing that 10 doesn't fall within the magic range of 11, and so even this super user who knew what's going on behind the scenes, at least the first attempt to find something that would run failed. Here's what the super user would actually have to do. And in order to construct this, what I did was I replicated the database on an unsecure machine, ran sample queries through the optimizer until I could, to get a feel for what plans were being run, both with a legitimate query and then with some sample attacks. And I found that I had to throw in some extra casts inside the query. Not that the casts do anything, but they magically increase the where clause size to 11 from 10. And now, as expected, when I run through this, it works. So yes, we know we can't stop everything, but I think it's taken the super user a lot of inside knowledge. They have to know the exact schema of the database. They need to be able to set it up on some machine under their control with data that looks pretty legitimate in order for the statistics to look right. And they have to be able to then run all of these tests. And as they're testing their procedure to see if they actually got it right, each one of those things is putting a flag into the log, and hopefully somebody on the security side is watching those logs and saying, wait a second, why is one of our admin getting disconnected 50, 100 times? I probably got booted out of the system about 100 times before I found an attack that worked. And if security wasn't calling me to say what was up by then, we got bigger problems inside. So that was a look. Hopefully, I've convinced you that at the very least we're on to something interesting in terms of identifying these anomalous, this anomalous activity. So when will this work, and when are you going to run into some trouble? So right now, the first caveat is we plug directly into the query processor. We've been using Postgres as our engine of choice because we have access to all the source code, and it's got a pretty good optimizer for us to play with. But that requires that we do have access to the source code. Our next iteration, and actually this changed since last Friday, our current iteration is deployed as an Oracle appliance. So all of the queries have to get channeled through this appliance. So it's an appliance that either lives on the same box but intercepts all of the queries as they come in, or it lives on a different box. They all get channeled through this appliance. As I mentioned before, this requires that you have this inter-process communication. So it's roughly twice the optimization cost. That could be a concern. There's also a security implication. If you're running the appliance, the trusted insider is going to know you're running the appliance. They're not going to connect to the appliance. They're going to try to connect directly to the database, and no amount of monitoring from outside the database is ever going to help you there. The other big caveat is the assumptions that we made. The first assumption is we assume that we have access to some sort of query workload. Now this can be because you have historical logs of known legitimate activity. If you're relying on that, you better have some way to verify that what you're looking at really does constitute legitimate activity. So there's a bit of a chicken and egg kind of problem going on there. What I'd actually recommend would be to obtain performance tests. So the people who are putting the system together hopefully have a development environment as well as a production environment. On the development environment, you're going to be running a whole bunch of tests to make sure that you can meet the demand that's going to be put on the production system. Those are all going to be, or at least you know which ones of those are legitimate queries that you want to go through. You can collect several thousand of these from the performance tests and use those. If you miss something that should be allowed to actually run, that means your performance tests weren't as representative as you thought they were, and you can go back to the team and say, hey, you need to add some more production tests, or they are representative and now you get good profiles based on that workload. And the last little wrinkle is we're expecting there to be a predictable workload. So we're talking here about transaction-style databases. Things where you're doing pretty predictable workloads. We're not looking at business intelligence applications. Business intelligence applications support a lot of ad hoc queries. A lot of times one query does not look like anything you've ever seen before, and if that's the sort of workload you have, no sort of anomaly detection is really going to help with a security issue because you're in a case where everything is anomalous, and it doesn't really matter how clever your techniques are. So just to wrap up and leave some time for questions or comments or clever ideas that you have that I've missed. First off, I hope I convinced you that relational databases are an important thing to protect. They're sitting behind many of our applications, and if you're not careful, it's not too hard to get a lot of information out of them. So we've got to secure these databases. We've got to do so both against the outsiders, who are largely the easier ones to protect against. You also have to protect against the insiders. So the approach that I've shown is first we build profiles of legitimate queries using this cross-feature analysis. And then as incoming queries arrive, we compare those against the profiles and detect anomalies. In most cases, we think those anomalies are things that are illegitimate activity. So this works against SQL injection, as I mentioned. It also helps protect against the insider threat, as well as many other forms of attacks. In terms of where we're going next, the first step we have to do is a red team exercise. So we've done this with some real attacks by a security team, and that only really leveraged what they were trying to do. They weren't actively trying to bypass all of the security mechanisms. So we'll set the whole thing up. But this time, we'll turn it over to anybody inside our company who wants to try to break in, and we'll put it on an unsecure OS. We'll make sure that the security on the web application is also unsecure. Basically, give them all of the benefits and see how often we're able to stop the attacks nonetheless. And then starting in October, we'll start looking at adapting these techniques to modifications where people are actually trying to update things or delete things, drop tables, all sorts of shenanigans. So let me wrap up with that, and I think I have just about 10 minutes for any sort of questions or comments.
Are there any questions?
Please use your microphone.
Yeah. Please use your microphone. Press the button on your microphone. Ask the question.
One of the important aspects of security is not about
only about preventing attacks, but also usability of the security.